Okay, so okay, we're recording now. Any issues or any questions that we have before we start the class? All right. Okay, so let's discuss the schedule then. All right, so I sent an email out with some class links, including some links we will look at today. All right, now, as I openly admitted, these next couple of weeks are going to be very tough for grading. It's a big crunch for me here, literally in terms of scheduling for the department and all that. But I have a big breakthrough once I can fall back on my spring videos. So I'll be able to get some grading done and catch up on the grading end of September and early October. And I hope I can get your homework 1 done by the time the homework 2 is to be due. The homework 2 is going to be due Tuesday, October 6th, the day after our main homework session. And homework 2 will cover lessons 11 through 18. We're going to start with lesson 11 today. We're going to have a lot of fun today because I have a bunch of neat stuff and videos. We'll play some games, literally play some games regarding gambling and probability, although no money will be involved. Sorry. All right. So any questions before we go on? The homework 2 will cover lessons 11 through 18. That homework will be due Tuesday, October 6th. Of course, we'll discuss the homework a couple of sessions before that. As for the homework 1, I hope to get that graded sometime by late September. Again, it's going to be a tough slog these next couple of weeks for me, but then the grading pictures will look a lot better starting at the end of September. Okay, so I do apologize for that delay. All right, any questions? Any questions? We're going to start part 2 of the class today. Any questions? All right, so let's go ahead and start.
Hi, everyone. Let's start talking about probability, which is a fascinating subject in and of itself, especially if you love gambling and games of chance. But probability also provides the mathematical foundations, the solid mathematical foundations of the subject of statistics. So we're going to start with discrete probability, as opposed to continuous probability, which we'll talk about later on. How do we work with probabilities when the number of possible outcomes is countable? Like, for example, when you roll a die, there are 6 possibilities. You can roll a 1, a 2, a 3, a 4, a 5, or a 6. It's not like probabilities involving weights or heights, where you can have a continuum of possible values. The French mathematician Laplace once claimed that probability theory is nothing but common sense reduced to calculation. This is true many times, and we're going to rely on this idea as we introduce probability, but it's not always the case. There are surprising situations where probabilities actually go against common sense, but the probabilities are correct. Sometimes the common sense is wrong. In lesson 11, we're going to start talking about the basics of probability. An event and how likely is an event. That's a probability. Part A, events and probabilities for those events. An event is something that either occurs or doesn't occur. And we often use capital letters, such as A, B, and C, to denote events. For example, an event A could be something like, it rains in my neighborhood today. That either happens or it doesn't. Or an event could be, the die comes up a 4 after it is rolled. Again, that either happens or it doesn't. So for an event, we can assign a corresponding probability, although we're going to talk about the way that we can assign this probability later on. But in principle, we can assign a probability to this event occurring, denoted by P of A. P of A must be a real number between 0 and 1. I say real as opposed to I or 2I. It must be a real number between 0 and 1, inclusive. So the probability of an event A could be 0, it could be 1, or it could be any real number in between, 1/2, 1/3, 0.99, whatever. In fact, you can think of a scale for P of A. If a probability is 0, it means that the corresponding event is impossible. Although that's a powerful thing to say. If I were to ask you, what's the probability that Kanye West will be the next president? You might say that it's very low, maybe 10 to the negative 10th, but it's not impossible. Likewise, it's a powerful thing to say that something is certain to happen. I mean, whether you're a fan of President Trump or Joe Biden or whichever presidential candidate, what's the probability that your favorite candidate will win? If you're honest, you're not going to say that the probability is 1. That means certainty. A probability of A happening is 1 if and only if A is certain to happen. Be honest. If the probability of A happening is 1/2 or 0.5, then that's the idea of a 50-50 chance. That's the idea of the probability of a fair coin coming up heads, or the probability of that coin coming up tails. We'll talk about the idea of a fair coin later on. And again, a probability could be other numbers like 0.9, 1 out of 3, and so forth. 1/3. Okay, now, if an event A does not occur, then that means the event not A occurs. So for example, if we roll a die, then event A could be the die comes up a 4. The event not A means the die does not come up a 4. So either A occurs or not A occurs, meaning A does not occur. The event not A is called the complement of A, which is denoted by A bar or A with a C superscript. Now remember, probabilities add up to 1. So the probability of A plus the probability of not A, or A complement, must be 1. The sum of the probabilities must be 1. You can think of the area of this pie, this disk, as 1. And then the probabilities for A and not A represent proportions of that total 1 area. So again, the probability of A happening plus the probability of the complement of A happening has to be 1. And we denote the complement of A by either A bar or A with a C superscript. So the probability of not A happening over here, I could have just said not A. The probability of A plus the probability of not A is equal to 1. Either A happens or not A happens, the complement. Now, if you solve for P of not A, and you subtract P of A from both sides, we get that the probability of the complement of A, not A, that is the probability of A bar, or the probability of A with the C superscript, that probability is 1 minus the probability of A. Again, the probability of not A, or the complement of A, is 1 minus the probability of A. So for example, if the probability that event A happens, where A is the event, it rains in my neighborhood today. If the probability that it rains in my neighborhood today, if the probability that A happens is 0.3, then the probability that it does not rain in my neighborhood today is going to be given by 1 minus 0.3, or 0.7. These complementary probabilities have to add up to 1. 0.3 and 0.7 have to add up to 1. I don't care if you put the 0 in front or not. One advantage is that it helps people remember that there's a decimal point there. But the 0 in front is optional. Now, how do we round off probabilities? Well, sometimes in math, we prefer exact values. And exact values are more often written as fractions. But in general, probabilities may be written as fractions or decimal numbers. Percents are also possible, but they're a bit more controversial because sometimes students mess up the math with percents. Now, I will tell you how to round off things in a typical problem, but when in doubt, we often round off probabilities to 3 significant digits or significant figures, sig digs or sig figs. And what's an example of something being rounded off to 3 sig digs or sig figs? Well, if you see 0.333, that's an example of a decimal written out to 3 decimal places or 3 significant digits. 3 significant digits. Also, something like 0.00703 or 0.703%. Now, remember, when you're dealing with significant digits, take a look at a blown up version of the number here. We don't count the 0 to the left of the decimal point. We never count that. In fact, you don't even have to write that down. Now, if you're counting decimal places, you do count the zeros in red over here, in addition to the digits after the zeros. So we would say that this number is written out to 5 decimal places after the decimal point, 1, 2, 3, 4, 5. 5 decimal places. However, if you're counting significant digits or significant figures, which is probably more common, then you would not count these zeros in front, even after the decimal point, at least the zeros immediately following the decimal point, but you would count the 7. You would count this 0 because it's following a significant digit. 7 is a significant digit. Any zeros following a significant digit would be counted. And you also count the 3. In fact, the 3, even if that were a 0, you would also count it. So if it's 0.00703 or even 0.00700, we would say that this is written out to 3 sig digs or sig figs, 3 significant digits or 3 significant figures. All right. Now, if we need final answers to be rounded off to say 3 sig digs or sig figs, then make sure that you round off intermediate results. Well, either state them exactly or round them off to more sig figs, maybe at least twice as many. So if we ask for at least 3 sig figs in your final answer, then we might want at least 6 sig figs in intermediate results. Certainly, if we want something written out to 3 sig figs at the end, you don't want to just round off to 1 or 2 in the middle. Even 3 might be a little risky. So at least twice as many or 6 might be the safer bet. Even safer would be to carry exact fractions such as 1/3, but sometimes that's not practical. Now, if you're dealing with a probability close to 1 or 0, you may want more than 3 sig figs if a probability is close to 1 or 0. So for example, if a probability is 0.99999987, then you may not want to say the probability is 1. That would mean certainty. You might actually want to sync this to many sig figs. The same is true for a probability close to 0. The probability that Kanye West will be elected president may be something like 0.00001, but it's not quite 0. Again, it's a powerful thing to say that an event is either impossible or certain, so you might want to take it out to more sig figs. All right, so we've talked about some of the rules for probabilities, but now how do we judge these probabilities? Next time we're going to talk about ways to figure out or estimate these probabilities. Next time.
All right. So now would be a good time for, and actually this is going to be one of the longer videos I'm going to play. I'm going to play 2 parts from this great Vsauce video, which has some interesting ideas regarding randomness. And I'll send out links to these various videos by the end of the week, if not tonight. Okay, so let's continue on. We're going to talk about dice, and then we're going to roll some dice, at least electronically.
Hi, everyone. So we're going to talk about 3 approaches to probability, and we're going to start with the classical approach, which is best suited to introduce this topic and is also most related to games of chance and gambling. So a trial is an experiment such as rolling a die, flipping a fair coin, and so forth. A trial. While we're at it, why don't we do an example of a trial, rolling 1 die. Assume that the trial must result in exactly one of n capital N like population size, capital N equally likely outcomes, which I'll refer to as ELOs. That's not official, but I'll refer to them as ELOs, equally likely outcomes, that are simple events which cannot really be broken down any further. So, for example, when we talk about rolling one standard six-sided die, there are 6 ELOs, 6 equally likely outcomes. You can roll a 1, and some books get really cute. They actually draw a die face with a 1 on it. A 2, a 3, a 4, a 5, and a 6. So there are 6 equally likely outcomes corresponding to the first 6 positive integers. Together, the ELOs make up the sample space, S. So S is the collection of these ELOs. Again, these are all equally likely outcomes. S here is the sample space. We have 6 equally likely outcomes. Then for an event A, P of A, the probability of A occurring, is equal to the number of ELOs for which A occurs divided by the total number of ELOs, N. So for example, what's the probability that a standard six-sided die is rolled and we get a 4? We roll a standard six-sided die. What's the probability we roll a 4? Well, only one of these ELOs gets us a 4. We have a total of 6 ELOs. Right? As a shorthand, we're going to let P of 4 represent the probability that the die comes up a 4. Only one of the 6 ELOs gets us a 4, this over here. There are 6 possible ELOs, so the probability is 1 over 6, 1/6. If you look at it in terms of odds, the odds against a 4 happening are 5 to 1, because there are 5 ways of not getting a 4. 1, 2, 3, 4, 5. 5 ways of not getting a 4, and 1 way of getting a 4. So the odds against a 4 happening are 5 to 1. What's the probability of getting an even number? Well, how many of the 6 outcomes represent even numbers? Well, we have the 2, the 4, and the 6. So we have 3 of the ELOs getting us an even number. We still have a total of 6 ELOs. So the fraction is 3 over 6, or 3/6, which reduces to 1/2. Bear in mind that on the homework, I would not expect you to reduce fractions, although I do hope that you know that 3/6 is 1/2. I don't want you to go through the tedium of worrying whether a fraction is reduced or not. Now, the event even is what we call a compound event because it combines 2 or more simple events. So these are examples involving rolling 1 die. Now, what's more interesting than rolling 1 die? How about rolling 2 dice? And then things get a fair bit more complicated. That's next time.
Okay, so now we're going to roll some dice electronically. The guys on Vsauce, or the guy on Vsauce, Michael, he mentioned random.org, and I want to take you to this site. I guess I should. Should I pause? I guess I should pause. Okay, it's a fun day today. I'm not encouraging you to gamble, by the way.
Hi, everyone. When we talked about rolling 1 die, we could represent the sample space of 6 equally likely outcomes as a rectangular array with 6 equally sized rectangles, each representing an ELO. 1, 2, 3, 4, 5, and 6. Now, if we're rolling 2 dice, what would be a good way of representing that sample space? If we roll 2 dice. Well, actually, it turns out to be better to distinguish between the 2 dice. If we call one of them, let's say, a red die, and the other one, let's say, a green die. Maybe we color the dice. Or we roll the dice 1 by 1. We have a first die and a second die. But it's not a good idea to just think of 2 white dice being thrown simultaneously. Then it's a harder problem to figure out the probabilities. we roll 2 standard 6-sided dice. Again, it turns out to be far more convenient if we distinguish between the dice. For example, color one die red and the other die green. By the way, one thing to think about, even though the red die has the 6 faces as equally likely, and the green die still has the 6 faces as equally likely, are dice totals equally likely? Is a 2 as likely as a 12 when it comes to the sum of the results on the 2 dice? If not, what are the least likely totals? What is the most likely total? So, once again, what would be the best way to represent the sample space for rolling 2 dice? 1 red, 1 green. Let's use a 2-dimensional table. Our simple events here are not going to be simple numbers attached to rectangles, like the 3 for this or the 4 for that. Our simple events here are going to be ordered pairs of the form R comma G, where R is the result on the red die, and G is the result on the green die. So for example, the sample space consists of everything from 1 comma 1, where we have a 1 on red and a 1 on green. That corresponds to snake eyes, where a 1 appears on both dice. All the way up to 6 comma 6, which is boxcars, where a 6 appears on both dice. But in between, we might have results like these. For example, 1 comma 2. That means we have a 1 on red and a 2 on green. A 1 on red and a 2 on green. Now bear in mind, that's different from getting 2 comma 1. A 2 comma 1 is when you get a 2 on red and a 1 on green. This is one reason why it's better to think of 2 differently colored dice, or thinking about rolling the dice 1 by 1. A 1 comma 2 outcome is different from a 2 comma 1 outcome. Both are equally likely though. In fact, when you think of all of the equally likely outcomes, there are 6 times 6 or 36 equally likely outcomes, each corresponding to the 36 ordered pairs that are implied to be in this table, from 1 comma 1 all the way over to 6 comma 6. 36 equally likely outcomes corresponding to 36 ordered pairs. Again, things like 1 comma 2 and 2 comma 1, these are different outcomes. 36 equally likely outcomes, each corresponding to an ordered pair. Order can matter. But these are equally likely outcomes. Each of these outcomes can happen with probability what? Well, for example, what is the probability of getting 4 comma 2, a 4 on red and a 2 on green? Well, how many of the 36 ELOs corresponds to a 4 comma 2? Just 1. 1 ELO corresponds to the event over here. There is 36 total ELOs, so the probability is 1 over 36. Again, 4 comma 2 only applies to this outcome over here. 4 comma 2, a 4 on red and a 2 on green. It only corresponds to one position in this grid. But there are 36 total positions, 36 total ELOs, so the probability of getting a 4 on red and a 2 on green is going to be 1 over 36. We'll talk about other ways of computing that. Notice that 1 over 36 is 1/6 times 1/6. That's not a coincidence. There's a rule for that. So this ELO is all alone, all by himself. But now, what if we consider the probability of getting a 2 on the red die? What's the probability of getting a 2 on the red die? And there are a couple of ways of figuring this out. Well, one way to figure it out is noticing that when we get a 2 on red, that means that we're going to get maybe 2 comma 1. We could get 2 comma 1 or 2 comma 2 or 2 comma 3 or 2 comma 4 or 2 comma 5 or 2 comma 6. There are 6 ELOs in this row. 6 ELOs in this row. All of them correspond to when we get a 2 on the red die. There are 36 ELOs, so that corresponds to 6 over 36 as the probability, which reduces to 1 over 6. But what's an easier way of figuring that out? Well, if we're worried about the probability of getting a 2 on the red die, does the green die matter at all? No, it doesn't. The green die doesn't matter at all. So we may as well go back to the 1 die case and think, well, what's the probability of getting a 2 on red? Okay, here's the sample space for the red die. It's 1 die. Well, we have 1, 2 out of 6 possibilities, 1 over 6. And that's an easier way to think of it. So remember, you want to be clever. So even though we are talking about 2 dice, it turns out that for here, on this problem, instead of thinking of it as a 2 dice problem, it's easier and more clever to think of it as a 1 die problem. What's the probability of getting a 2 on 1 die? Who cares about the green die? All right, next. Again, how could you have answered this very quickly? Think of it as a 1 die problem. Now, what about this? We get doubles if both dice come up the same number. Like, for example, snake eyes, 1 comma 1, 1 comma 1, that's doubles. Also, boxcar, 6 comma 6. These are examples of doubles. What's the probability of getting doubles? Take a look at this grid. What is the probability of getting doubles? How many of these ordered pairs are going to be doubles? And what is the total number of ordered pairs, once again, in this table, in this grid? Well, how many doubles are there? We have 1 comma 1, we have 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, and 6 comma 6 boxcars. So everything from snake eyes to boxcars, if we look at the main diagonal here, 1, 2, 3, 4, 5, 6. 6 of these ordered pairs correspond to doubles. Over, how many ordered pairs do we have total in here? We have 36. So the probability is going to be 6 over 36, or 1 over 6. 1 over 6. Now, there's another way of figuring this out. The 1/6 might imply that there's a more clever way to think about this, and there is. Think about this. Assume that the red die is rolled first, and then the green die is rolled second. Let's reframe the problem. Whenever the red die comes up, whether it's a 1, a 2, a 3, a 4, a 5, or a 6, what's the probability that the green die is going to match the red die? That's when you get doubles, right? When the green die matches the red die, whenever the red die comes up. That's going to be 1/6. The probability that the green die matches the red die will be 1/6. That's exactly the probability of doubles. Let's think it through. Well, I'll keep the circles here. If you get a 1 on red, that means that you need a 1 on green in order to get doubles. Let's say you win if you get doubles. If you get a 1 on red, then to win, you must get a 1 on green. What's the probability you get a 1 on green? 1 out of 6. Think of it as a 1 die problem. If the red die comes up 2, well, to get doubles to win, you need the green die to come up 2. What's the probability of getting a 2 on green? Again, 1 out of 6. It's a 1 die problem. So whenever the red die comes up, it could be a 3, it could be a 4, and so forth. The green die, what's the probability the green die matches up? Like, for example, 4 and 4. what's the probability the green die matches up is going to be 1 out of 6, whatever the red die comes up. This thinking will help later on when we consider other probability problems. The probability that the green die matches the red die is 1/6, regardless of how the red die turned up. This kind of thinking will help us later on. And again, it's a more clever way of answering this question without having to go through it brute force and counting all the doubles cases.
All right. Okay. Well, any questions before? I'm going to pose 4 problems here. Really, yeah, kind of 4 problems here early on. Any questions before? Any questions before? Any questions? All right. We're going on. Okay.
Hi, everyone. Now let's consider the following questions about dice totals or sums. Try to answer the following questions. What are the least likely totals or sums on the 2 dice? I should say possible. What are the 2 least likely possible totals or sums on the 2 dice? Yes, the probability of getting a sum of 0 is 0. That's true. But what are the least likely possible totals or sums on the 2 dice? Also, what is the most likely total or sum on the 2 dice? So what are the least likely possible sums? What is the most likely sum? Regarding the most likely, and by the way, follow-up questions, what are their probabilities? What are their probabilities? While we're at it, what's the probability that the total or sum on the 2 dice is a 5? Find the probability that the total or sum of the 2 dice is, let's say, 5. And by the way, what are the possible sums? A little hint here. What are the possible sums? The integers from 2 through 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. I'll give you a minute to think about these 4 questions. And I'll give you a hint. Try to focus on this grid here, this 2-dimensional representation of the sample space for the outcomes when you roll 2 dice. Imagine filling these entries with sums. All right, question number 1. What are the least likely possible sums or totals on the 2 dice? In this corner over here, 1 plus 1 is a measly 2. 1 plus 1 is 2. That's when you get snake eyes. Snake eyes represents the one possible way of the 36 that you can get a 2. And by the way, the corresponding probability is 1 over 36. So the probability of getting a sum of 2 is 1 over 36, because only one ELO, only one ordered pair out of the 36, namely the ELO corresponding to snake eyes, 1 and 1, will lead to a sum of 2. So the probability is 1 over 36. Similarly, over here, boxcars. That's the only ELO that leads to a sum of 12. 6 plus 6. So the 2 and the 12 are both least likely. The probability that you get a sum of 2 is 1 over 36. Also, the probability that you get a sum of 12 is 1 over 36. So 2 and 12 are the least likely possible sums for the two dice. They both have probability 1 over 36, corresponding to these two corner entries, these two corner ordered pairs. So we've answered number 1 and part of number 3. Number 2, what is the most likely total or sum on the two dice? Well, imagine filling out this table or grid here. What's the longest skew diagonal here? The longest skew diagonal? Well, take a look here. How can we get a 7? 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. This is the longest skew diagonal going from lower left to upper right. How many 7s do we have along here? We have 6 of them. So the probability you get a sum of 7 is 6 over 36, also known as 1/6. And by the way, what's a more clever way of figuring that out? And I'll give you a hint. It's similar to the analysis of doubles. Remember that the probability of getting doubles was also 1 over 36.
1 over 6.
The reasoning here is similar. What's the reasoning? Well, think of it this way. Like in the doubles example, right? What was the probability of getting doubles? It was 1 out of 6. Why? Because regardless of how the red die turned up, there's exactly one way for the green die to match it. If the red die came up a 3, there's a 1 in 6 chance that the green die also came up a 3. If the red die came up a 4, there is a 1 in 6 chance that the green die also came up a 4. Okay, 1 in 6. So regardless of the result on the red die, there was a 1 in 6 chance that the green die could match it. Well, similarly, what if the red die came up a 1? What's the only way that the green die could come up so that you get a sum that was 7? So you're aiming for a sum of 7. If the red die comes up a 1, what do you need on the green die? You need a 6. Likewise, if the red die comes up a 2, what does the green die have to come up as? A 5. If you get a 3 on red, you need a 4 on green. 4 on red, 3 on green. 5 on red, 2 on green. 6 on red, 1 on green. So regardless of how the red die turns up, there's exactly one way for the green die to turn up that will give you a sum of 7. It's really a one die problem, just like with doubles. With doubles, you're asking for the probability of a match. In the sum of 7 case, or sum equals 7 case, you're asking, well, what's the probability that you get a result on the green die such that when you add it to the result on the red die, you get a 7? Well, again, there's a 1-to-1 matching here. Regardless of how the red die turns out, there's exactly 1 out of the 6 results on the green die that will get you a sum of 7. So by a similar analysis, the probability is 1 out of 6. For doubles, it was 1 out of 6. For a sum of 7, it's 1 out of 6. It's the skew diagonal this time. So this is like the doubles diagonal here. This is like the sum of 7 diagonal. Regardless of how the red die turns out, there is exactly one result on the green die that will get you what you want. All right. What about the probability that the sum is 5? I don't have such a cute way of showing that, but what's the probability that you get a sum that's 5? Imagine filling out some of these sums here. Well, think about the various ways to get a 5. How can you get a 5? How can you get a 5? Erase these over here. Well, you can get a 4 and a 1, also a 1 and a 4, because the order matters, a 3 and a 2, and also a 2 and a 3. There are 4 ways of getting a 5. Some students may have started with the snake eyes case over here, the sum is 2, and then get the other skew diagonals. Here's how you get a 3, here's how you get a 4, and, well, here's how you get a 5. There are 4 ways to get a 5. 4 over 36 is 1 over 9, or about 11.1%. Again, I do not expect you to reduce fractions. I'll accept this as a final answer. Again, the probability of getting a 7 is 1 out of 6. So, to answer the questions, what are the least likely possible sums or totals on the 2 dice? The least likely possible sums, 2 and 12. They both had probabilities that were 1 over 36. So 1 over 36 for the 2, 1 over 36 for the 12. What is the most likely sum or total? The answer to that was 7. The probability of that was 6 over 36, or 6 over 36, or 1/6. And there was a more logical way of thinking that through. Whatever the red die comes up as, there is exactly one way for the green die to set up a total of 7. So we've answered number 3 as well. What are their probabilities? 1 over 36, that was the minimum possible probability among these. 1 over 6, or 6 over 36, that was the maximum possible probability among these. The probability that the sum or total is 5 was 4 out of 36, or 1/9. 4 over 36, or 1/9. I can't really think of a cute way of coming up with that, except for filling out this piece of the table. All right, so we've thrown lots of dice. Let's now consider roulette.
And I had fun combining some videos for roulette, of various sources for roulette. But it's good to show what roulette is. Again, I'm not encouraging you to gamble, but it's pretty standard in a probability or stats class to see what these things are. All right, I got to pause this. I have some interesting videos to show you, including a clip from a favorite action film of mine from the late 90s, Run Lola Run.
Hi, everyone. Let's say you're brave and you take a trip to Las Vegas. You decide to play roulette. You go up to the roulette table and you see on the roulette wheel 18 red numbers, or red slots, and 18 black numbers, or black slots. Let's say you bet $1 on red. Now, don't laugh. I know that a casino would laugh at you for betting $1, but let's say—
Sorry, I gotta restart. I didn't close caption.
Take a trip to Las Vegas. You decide to play roulette. You go up to the roulette table and you see on the roulette wheel 18 red numbers, or red slots, and 18 black numbers, or black slots. Let's say you bet $1 on red. Now, don't laugh. I know that a casino would laugh at you for betting $1, but let's say, hypothetically, you bet $1 on red. Well, if the wheel comes up a red number, or if the ball falls into a red slot, same thing. Basically, if the ball falls into a red slot, it means that that red number comes up on the wheel. Then you win, and you get your $1 back, and you get $1 on top of that. So you win a net gain of $1. However, if the roulette wheel comes up on a black number, for example, then you lose your $1. You're out $1. Now, is that a fair deal? If you bet a dollar on red. If you win, you get a net gain of $1. Is that a fair payoff? The answer is no. Guess what? Casinos are in it to make money. It's not just the players, the casinos are there to make money. What tilts the odds against you? What slightly tilts the probabilities against you?
What's the answer to my question? 18 red slots, 18 black slots. What slightly tilts the odds against you in the color game? Right. Why not? Why not? And why is Europe a bit nicer than America? That's also true of, that's also true of the healthcare systems. The green numbers. Yes, right.
It's those two green slots, 0 and 00. Actually, in Europe, they're nicer because they only have one green slot. But in America, we're not as nice. There are two green slots that could mess you up even more. So why do the two green slots mess you up? Because the total number of numbers that are available on the wheel, the total number of slots on the wheel is not 36. It's not 18 plus 18. It's 18 plus 18 plus 2. And the sum of 18, 18, and 2 is 38. The probability that the wheel comes up red is 18 over 38, or 9 over 19, about 47.4%. Same for black. And the probability of getting a green number, 0 or 00, is about 5.26%. But those two green slots, that tiny percent, slightly tilts the odds against you. It's not a fair game. $1 would not be a fair payoff if the wheel comes up red, because the probability here is a bit less than a half. If you only had the 18 red slots and the 18 black slots, then a $1 payoff would be fair for a $1 bet if you bet on red, because then the probabilities would be 50-50, 50% versus 50%. But actually, in order for this to be a truly fair game, we'll see this later on when we talk about expected value. If you bet $1 on red, then really, because of this percent that's a bit below 50%, a fair payoff would actually be more like $1.11. The casino pays an even money payoff for red-black bets. In other words, every dollar bet is matched by the casino if the player wins. But this is slightly unfair to the player, to you, because a fair payoff would not be $1, it would be $1.11 for every dollar bet. But see, the fact that the payoff is only $1, that ensures that the casino makes a profit in the long run. And what ensures that is something called the law of large numbers, what I'll call the LLN. The idea that probabilities built into the game will crystallize in the long run. So in other words, the observed relative frequencies of red, black, and green results, if, for example, imagine a gambling addict were to play this game 1,000,000 times, all right, then you're going to pretty much see these probabilities come up as relative frequencies. The relative frequencies will be very close to the theoretical probabilities in the long run, that is, over many plays of the game, say 1,000,000 plays. Again, the observed relative frequencies over like 1,000,000 plays, okay, of red, black, and green results will approach the corresponding theoretical probabilities. These in fraction form, these in percent form. So in the long run, over 1,000,000 plays, you're going to see about 47.4% red numbers come up, about 47.4% black numbers come up, about 5.26% green numbers come up. Right. So in the long run, on average, the casino will make a profit of about 5.26 cents for every dollar bet made by players who bet on either red or black. And that comes from the fact that there's about a 5.26% chance that the roulette wheel will come up green as opposed to red or black. So we call that the house advantage. It's 5.26%. In fact, it turns out that it's not just for one number. If you bet on groups of numbers, this is often the kind of house advantage you see for roulette, for various types of bet. All right. Now think about this. What is the best way to maximize your chances of winning a huge amount of money in Vegas, in any game, given that in the long run, the probabilities are meant to work against you? In the long run, the probabilities are meant to work against you. The probabilities will crystallize in the long run, and the payoffs are set against you in the long run. How do you maximize your chance of winning a huge amount of money? You need $1 million to pay someone off. What's the best way of doing it, probability-wise?
What do you think? So you need to make a lot of money. What may be the best strategy if you need to make a lot of money? Remember, the worst thing to do is being the gambling addict, right? Too many trials. What's the opposite of that? How about this?
Yeah, I think the best way of doing it, put it all in one shot and hope. Really, really hope. Now, speaking of the law of large numbers, here's an example with coins. These are computer simulations of coin flips, assuming a perfectly fair coin. The law of large numbers guarantees that theoretical probabilities will crystallize in the long run in the observed relative frequencies. The observed relative frequencies from repeated trials, like 1 million trials or 1 billion trials, think of 1 million or 1 billion plays in Vegas. The LLN says that the observed relative frequencies will approach the corresponding theoretical probabilities as the number of trials approach infinity. So over many years, the casinos expect to make money. Donald Trump critics will joke otherwise. In each column below, we simulate the flipping of a fair coin, in the red column here and the blue column here. So if we first consider 10 flips, then 100 flips, then 1,000 flips. Again, these are computer simulations of a fair coin. So for example, in simulation 1, so a fair coin is flipped once, it comes up tails. In the vertical axis, that describes the relative frequency of heads. So if you flip a fair coin, all right, let's say it comes up tails, then you've gotten 0% heads so far. If you flip the coin again, the computer flips the coin and it comes up tails again. So far, again, 0% heads. But then the computer flips a head. 1 head out of 3 flips, the relative frequency of heads so far is 1/3. So we're tracking the relative frequency of heads so far. Then the computer flips the coin again, gets another head. 2 heads out of 4 flips, the relative frequency of heads is 1/2 or 0.5. And so on. Now look what happens after 100 flips of the coin, and then 1,000 flips. It looks like the relative frequency of heads is really approaching what number? It looks like it's really approaching 1/2 or 0.5. It's approaching this flat line. The law of large numbers says that in the long run, the observed relative frequencies will crystallize towards the probabilities. The probability of a fair coin coming up heads, by definition of a fair coin, is 1/2 or 0.5. The relative frequency of heads will approach 0.5 in the long run. Here's another simulation. It's a repeat. Well, it's a repeat of the idea, but the computer flips the coin 10 flips, 100 flips, 1,000 flips. Now we're getting a different sequence, but still in the long run, we're getting about 50% heads in the long run, even though the particulars are different compared to the red simulations. So again, in the long run, the law of large numbers says that the observed relative frequencies will approach the theoretical probabilities. Hi, everyone. Let's say a small town is planning a parade for next July 4th, and they might want to ask and estimate what's the probability that it's going to rain in our small town next July 4th. Well, what might be a way for this town to estimate the probability that it's going to rain next July 4th? Well, let's say that they have 100 years of weather records. What could they do? They could look back at the last 100 July 4ths, count up on how many of those July 4ths it rained, and then divide by 100. Now, that wouldn't take into account issues like climate change, for example, but that seems like a fairly straightforward approach. And that would be an example of the frequentist or empirical approach, what we've seen in practice. Let n be the total number of trials observed. For example, the most recent 100 July 4ths in the small town and their weather records. So if n is large, well, let's say 100 is large enough. Bear in mind, if it had rained this past July 4th, I don't know if we want to say that there's a 100% chance of rain next time around. But let's say that n is big enough, 100 might be big enough. Then let's estimate P of A by the number of trials in which A occurred, the number of years for which on July 4th it rained in that town, divided by 100. The number of July 4ths for which we have records. Here's another example. Let's say that a magician gives you a coin, and you'd like to know if the coin's fair. So you flip the coin, and you get heads 255 times, and tails 245 times. Estimate the probability of heads for the coin. Now, is that probability going to be 255 over 245? A lot of students would say something like that. And the answer is no. First of all, there's no way because, first of all, that's a number greater than 1. That makes no sense to the probability. Make sure that you don't make a mistake like that on an exam or something like that. Probabilities cannot be greater than 1 anyway. No, no, no. In order to find or estimate the probability the coin comes up heads, P of H, we're going to estimate P of H, the probability the coin comes up heads on a flip. First, you have to calculate the total number of times the coin was flipped. 255 plus 245 is 500. That's n. So our estimate for the probability the coin comes up heads will be 255 over 500, or 51%, about 51%, 0.51. That's our estimate for the probability that the coin comes up heads. Now, what we might ask later on when we do statistical inference is, well, is there strong enough evidence that the coin cannot be fair? Or can we chalk this up to sampling error, for example? That's the kind of question we'll ask later on in the course. Bear in mind, if it is in fact a fair coin, then in the long run, after a million flips, a billion flips, if you really have no life, then the observed frequency of heads will approach the theoretical probability of 1/2 or 0.5, if the coin is in fact fair.
By the way, it's relative frequency.
The estimate for P of H will approach 1/2 or 0.5 by the law of large numbers. And again, up here in red, my warning, remember to find the total number of times that we flip the coin. Find out the true value of n. 245 may help with the complement. The complementary probability will be 245 over 500. But for n, you need to add these to 255 plus 245. Okay, now let's say I ask you right now, think about who you favor for president in the next presidential election. Estimate the probability that that person will be elected president. I guess you could go to Nate Silver and 538.com, but I'm guessing you're going to go for more of a subjective approach. Basically, a hopefully educated guesstimate. Again, Nate Silver may try to do it a bit more precisely using polls, but off the top of your head, you're probably relying on a subjective estimate. In fact, one thing they do up in Silicon Valley, you have these Stanford graduates who have studied decision analysis, and they might actually ask a Silicon Valley CEO, what's the probability that you think such and such will happen? And they'll use this basic color wheel that you might find in kindergarten. And again, we can talk about the probability that your favorite presidential candidate will win the upcoming election. So you have this piece here in red, for example. And then the consultant might adjust a knob on the back, adjust the proportion of the wheel that's colored red, and the consultant might ask, so what do you think the probability is that your candidate will win the next election? Will it be like this, or like this, or like this? And then a number will appear on the back indicating what the corresponding estimate would be based on the proportion of the wheel that's colored red. It seems like something you might find in kindergarten, but they actually do this in decision analysis, visualizing probabilities. Because sometimes you might think that CEOs are more quantitatively oriented. Some of them may not know math or probabilities that well. All right. So next up, we're going to look at some rules regarding relationships between probabilities.
All right, so that's next time. Quickly, just a little funny clip about subjective probability. All right, so let's talk about the extra credits. Okay, so this will take a couple minutes. All right, so investigating randomness. So I'd like you to either take a small coin and flip it, or even nicer, go to the random.org site, random.org, https://www.random.org/coin/ I sent this out in the email. All right, so flip a coin, flip one coin. All right, select a coin top. You can choose your coin, but let's go ahead and go with an American penny. Let's be easy, an American penny. All right, flip the coin. All right, so I got heads. Now, whether this coin comes up heads or tails determines how you're going to go with the extra credit. Bear in mind, you'll get the 3 points whichever result you get. All right, but here are the rules. I got a head, so I got to follow the heads rules. Okay, so I flip the coin on random.org, atmospheric noise, right? If the coin comes up heads, here's what I go. Here's what I do. Tell the website to flip the coin 100 more times, or I actually manually flip a coin. I had my students do that in class. Record the results of the 100 flips on this sheet, okay, on here, or when you make up. You can just send me a text file with the sequence of 100 H's and T's, all right? Write an H when you get a head, write a T when you get a tail. In fact, I can do it right now. I can do it right now with, okay, so let me go back. Let me see here. Okay, 100 flips. I can do it right now. Of a penny, flip the coins. All right, so on my sheet, or I can just do it on some text file. It doesn't have to be my sheet, but put your name on it. Okay, tail, T, tail, T. So I write down T, T, H, 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 T, T, H, 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 T, T, H, T, T, H. You see? T for tail, H for head with Abraham Lincoln on it, all right? Or whatever your head is. Okay, so that's when it comes up heads. Now, what if random.org gave me a tail when I flipped the coin that first time? Then here's what you're going to do. This might be more challenging. Flip a coin 100 times in your head. You're going to offer me a simulation of what you think a sequence of 100 heads or tails look like based on a fair coin. Okay, after each flip, write an H when you get a head in your head. Write a T when you get a tail in your head. So write a sequence of H's and T's that you think looks random based on a fair coin. All right. And then again, record the flips on this sheet or a text file with your name on it. So if you put your name on something, you write down the sequence of H's and T's. Keep a record for yourself. Oh yeah, did I flip a head or a tail at the outset? What should I do? Did I go to the website, or did I sit, or did I make it up from my head? All right. So those are instructions. Remember what you did, if you did it from the website or did it for real, or if you simulated it in your head, write down the sequence, put your name on it, and we're going to discuss that. So bring it to class next time. We'll discuss it. You'll kind of grade it, and you'll all get the 3 points. Just grade it right, okay? And then email it to me, within a few days. That's the idea. All right. Any questions about the extra credit? And by the way, some of you might do something else. You might write down 100 H's or something. I even have a place for you folks, and you'll still get the extra credit. But I have a special place for you folks. No, that helps in our. I don't mean hell. I mean it's a special category which will help us in the game. So hey, now I hope not everyone does this, but if a student does like 100 H's, hey, that's part of the game. I hope you don't all do that. Any questions? Any questions? Let me go to chat. All right.
So I have a question.
Okay. Okay.
Basically, are we just choosing which one we want to do in our head or on the computer?
Oh, okay.
thing?
Now I do want you to go to random.org or actually take a real coin so that you know which group you're in, because I want it to be about half, right? So at the outset, either flip a coin for real or tell random.org to flip a coin once, okay? And then based on whether there's a head or a tail, follow the corresponding instructions. I want it to be about half. Now, granted, I could tell from when I did this in class that some people that it would be very different from one half, and maybe people kind of cheated. So we're going to kind of catch that also. But but the idea is that you go to random.org or take a real coin for real, flip the coin, and that'll tell you which group you're in. Okay. Before, I'd have students trade papers and they try to guess based on a rule what the other student did. We're not going to trade papers, all right, even electronically. Even though coronavirus does not pass electronically, I'll have you grade your own papers and we'll organize some statistics to see how good my rule is. My rule for discriminating between who got the head and who got the tail, first off. Yeah, the sheet is here. I also emailed it to you folks. So if you need it, you can email it to me. It's also on my class games and handout site, but I'll email it to you. Or remember, you don't need the sheet. Just get a text file. You can get your own text file or Word file, put your name on it, right? Give me the 100 H's and T's. Yeah, just tell me the coin flip. So basically, what you're going to email me is some E file with your name on it and a sequence of 100 H's and T's. Now, whether you get a head or a tail determines how you get that sequence. Are you going to go to random.org or maybe flip it for real? Or are you going to try to make it up in your head and try to fool me? You're going to try to fool me into thinking that you came up with a truly random head-tail sequence. That's the idea. Can you fool me into thinking that you flipped the coin when you actually didn't? That's if the coin came up tails. The simulation people. Which would you rather be in? Well, I don't know. Now with the website, before I think people wanted to make it up. But with the website, you might prefer the website. In fact, even if you get tails, you might want to go to the website and see for fun what you get. Any other questions? I'll stick around. Okay, so I'll stick around for at least another 5 minutes. Any other questions regarding the class today or the extra credit? Oh, the recording's still on. Any more questions until I turn the recording off? I'll turn the recording off in 15 seconds unless anyone says otherwise. You're welcome. Yes. Good to see everyone.
Thank you.
Okay, recording off. Okay, lesson 11. We did lesson 11 today. All right.